Welcome to Visual Algebra Lecture 3.1, Subgroups. A subgroup of G is any subset that is also a group. The set of all subgroups of G forms a lattice, and this will be one of our most useful visuals in the remainder of this course. We will learn how to spot a number of key features and properties of a group just by inspecting its lattice. There is a fluency to this that we will develop and hone throughout the course. Unlike Cayley graphs, subgroup lattices actually appear in most algebra books and courses, but usually only very sparingly. In this course, we will utilize them way more than any existing source does, and our collection of examples will be much deeper as well. In this lecture, we'll see the subgroup lattices of both groups of order 4 and of order 6. We'll also prove a few basic properties about subgroups, their intersections, their generating sets, subgroups of cyclic groups, and the so-called one-step subgroup test. Let's start by recalling the definition of a subgroup. A subgroup of G is a subset H that is also a group. We denote this with this less than or equal to symbol. If we write C2 is a subgroup of D3, that means there is a copy of C2 sitting inside of D3 as a subgroup. We must be careful, though, because there might be multiple copies. For example, the subgroup generated by F has two elements, and therefore is isomorphic to C2, as is the subgroup generated by RF. Some books will write things like Z3 is a subgroup of D3, and C3 is a subgroup of S3, but we will try to avoid this because Z3 is not even a subset of D3, technically, nor is C3 a subset of S3. Remember, Z3 consists of the elements 0, 1, and 2. Those are three numbers, whereas D3 consists of six symmetries of the square, which we can write as 1R, R squared, F, RF, and R squared F. So instead, we can write things like Z3 is isomorphic to the subgroup of D3 generated by R, and C3 is isomorphic to the subgroup of S3 generated by the permutation 1, 2, 3. One of the takeaways from this slide is that it is often, but not always, preferred to express a subgroup by its generators. So write things like the subgroup generated by R instead of Z3, and the subgroup generated by 1, 2, 3 instead of C3. Let's start by considering the subgroups of the two groups of order 4, V4 and C4. Each element of V4 generates a proper subgroup of it. And to emphasize what I mean by proper, I just mean that it's a proper subset. So it's a subset that's not the entire set. So H, V, and R both generate size 2 subgroups, and E generates just the trivial subgroup. And this is all the subgroups we have because these are all the elements, and if we try to use any two elements, not including the identity, we will get the entire group. With a little bit of thought, we see that there are three subgroups of C4. So there's the subgroup itself, the non-proper subgroup. It's generated by either R or R cubed. And then R2 generates a size 2 subgroup, and then 1 generates the trivial subgroup. It is illustrative to arrange these in a subgroup lattice. So let me just show you by example. I think it should be fairly self-explanatory as to what this means. So here are all the subgroups of V4. This is the largest one. It contains these three, and each of these three contain the trivial subgroup. And here's C4. So remember, these are subsets. So this contains 1R, R squared, and R cubed. And this just contains 1 and R squared. And I will sometimes put the order of these subgroups on the right-hand side. It's not required that we have all subgroups of the same order at the same level. I just think it's helpful to do so. Let's do another example, this time the integers mod 6. So here, and in any group, every element generates a cyclic subgroup. So 0, 1, 2, 3, 4, and 5 each generate a cyclic subgroup, but some of them generate the same group. And with a little bit of thought, we realize that these are all the subgroups that there are. In other words, any other subset not in here is not going to be an actual subgroup. Different choices of Cayley graphs can highlight different subgroups. So if we use the generator 1, we can see this subgroup right here sticking out at us. If we use the generators 2 and 3, then here's a Cayley graph, and we can see this subgroup of size 2 sticking out at us, and we can see the subgroup of size 3 around the outside as well. Here's a subgroup lattice. Here's how those subgroups are related to each other. So be careful, the smaller numbers go up top because 1 generates the entire group, whereas 3 just generates 2 elements. Remember, that's 0 and 3. Throughout this course, it will be essential to learn the subgroup lattices of our standard examples of groups. In many cases, you need to be able to construct them without looking. In other cases, for larger groups, you should at least be able to recognize which one of the two that I show you is the diquaternion group of order 16 and which one is the semi-dihedral group of order 16. Let's keep going and construct the subgroup lattice of the other group of order 6, namely the dihedral group D3. Remember that in any group G, every element, little g, generates a cyclic subgroup by definition. This is all powers of G, positive and negative. For small groups like D3, these are the only proper subgroups. And here are those proper subgroups. So R and R squared both generate an order 3 subgroup, and then all 3 reflections generate an order 2 subgroup consisting of the identity and the reflection itself. And then there's the trivial subgroup. Note that some subgroups are visually apparent in the Cayley graph. Here's the subgroup generated by F. You can see it right there. Here's the one generated by R. And then these two subgroups you really can't see as well in here. But in the cycle graph, because this is not a large group, you can actually see all 3 order 2 subgroups and the order 3 subgroup stand right out at you. And finally, here is the subgroup lattice. In general, it's hard if you have a bunch of subgroups to sort of see how they're put together. But here, this is small enough that there's one subgroup of order 3 and 3 of order 2, and they really have to sit together just like this. It's straightforward to show that for any collection of subgroups of G, their intersection is a subgroup. And I say collection because I'm going to index it over a set A, which could be finite, countably infinite, or uncountably infinite. And I say exercise because I'm not going to actually do this. I'll just give you an outline of how it goes. So you have to show 3 things. Show that it contains the identity, that every element has an inverse, and then closure. So how would this go? So the identity, we know that E is in every single H alpha because they are subgroups, and therefore E is in the intersection of all H alphas. By definition, that's what the intersection is. It's the things that are in every one of them. So what about inverses? So let's say that little h is in the intersection of the H alphas. Then H is in each individual H alpha, and which means that because each one is a subgroup, H inverse is in each big H alpha. And that's what it means for H inverse to be in the intersection of all the H alphas. Okay, I'll stop writing this thing on the bottom. Finally, I said I wasn't going to do the whole thing. I'll just do the whole thing. So closure, let's say that I'm going to use A and B. A and B are in the intersection of H alpha. So it's going to be very similar. Then A and B are in every single H alpha, which means that so A and B are in every single alpha. So A times B is in every single H alpha, which means that A, B is in the intersection of all the H alphas. That's what the intersection is. It's the set of all elements that are in every single one of them. Next, every subset S of G, not necessarily finite, generates a subgroup. And we're going to denote that with these angle brackets with S inside. By definition, this is the set of all finite words that are built from elements in S and their inverses. So I can write a finite word like this. So this finite word of length K, where each SI is an S. So we could have repeats, and each exponent is 1 or -1. So for example, if S is like A, B, C, then an element in here is in this is going to be A, C, B inverse, B, A, C, A inverse, something like this. And instead of length, well, length, when you write it like this, often you can shorten, you can turn that into the identity. But this is going to be the definition. We require words to have finite length, even if S is infinite. Here's an important proposition. For any subset S of G, I should probably say non-empty. I think that's assumed. The subgroup generated by S is the intersection of all subgroups containing S. So here's how we write that. Now, we're going to prove this, but I also want to explain what it means and why it's significant. So you'll see results like this in a lot of other areas of mathematics. Well, especially in algebra, but other algebraic structures. And let me try to give an example of this. So I like to say that this thing on the left is the subgroup built from the ground up. So we're taking all of the elements in S, and we're making all possible words from it like this, and we're building it from the ground up. Whereas this thing over here, we're taking S, maybe S consists of a bunch of points. I'm going to draw it like this, but again, S could be infinite. And we're going to take all of the subgroups, every single one of them. There's maybe H1, there's maybe H2, all the subgroups that contain it. And again, I'm going to index them with integers, but this index set could be uncountably infinite. So this is just a sort of a cartoon to get you to understand it. Maybe here, so here's H3, etc. We're going to take all of the subgroups that contain that and intersect them, and to claim that we get the same thing. So an analogy that you might be familiar with, or maybe if not, you can become familiar with it, is something called the convex hull of a set of points. So I'm going to do it in the plane. The convex, but it works in any number of dimensions. So the convex hull of a set of points in the plane is what you get if you put nails in these, and then you wrap a rubber, or you stretch a rubber band around the nails. But these are supposed to be straight lines. Sorry about this. And you stretch a rubber band around these nails. The convex hull is the region inside this. Now, there's a way to define the convex combination of a set of points. So the convex combination, let me say a bit about what that is. So if we have in the plane, or I don't need to draw the axes. If this is the vector, let's say x, and this is the vector y, and maybe 0 is up here. So the convex combination is the set of all vectors on this line. So it's what you would get if you put two nails here and put a rubber band around this. And we can parameterize this path here as t times y plus 1 minus t times x, where t goes between 0 and 1. So notice that if t equals 0, then we get 0 here and 1 times x here. So for t, so when t equals 0, we're right here, and then when t equals 1, now we have y times 0, so we are here. What we've done is we parameterize this path. If we want to do this with 3 points, kind of running out of room here, but you can imagine if you have 3 points here, and maybe the origin is down here, how do you describe the set of all points that are inside of here? Well, we can do a similar thing. We can say instead of t and s, I'm going to, well, instead of t and 1 minus t, I should say, I'm going to use t1 times, let's call this x, y, z, t1 x plus t2 y plus t3 z, where t1 plus t2 plus t3 is equal to 1. So that was built into that condition over here. T plus 1 minus t is equal to 1. Here we're going to force it. So when t1 is 1 and these things are 0, we're going to be at x. When t2 is 1 and the others are 0, we're at y. And when t3 is 0, we're going to be at z. And then if we have 3 values here that are all less than 1, we're going to be somewhere internal. So this is the convex combination. I'm going off on a tangent, but basically there are 2 ways to define the convex hull of a set of points like this. One of them is with convex combinations like this. You just do it for all possible points, even if there's infinitely many of them. The other one is to define this as the intersection of half spaces. So this is called a half space. This is a here's another half space. Here's another half space. So I'm drawing a bunch of half spaces that contain all of these points. And let me just draw these points extra dark so we can see them. So if I take every single half space, kind of running out of colors here, that contain these points that intersect them, I claim that I'm going to get the same region as well. Because we don't need this yellow half space, but we will get half spaces that go along every single edge that contain all the points. So we say that the convex hull of a set of points, which we can define as, from the ground up like this, as a set of convex combinations, is also the intersection of all half spaces that contain S. So you get this equality, one from the ground up, one from the top down. And the same thing over here. This is what you get from building the group element-wise in terms of words, and this is what you get by intersecting everything that contains this. You get this equality. And this allows us to say that the subgroup containing S truly is the smallest subgroup that contains S. The intersection of this literally is the smallest subgroup that contains S. Okay, so that's enough little exposition behind this, probably more than you asked for. But let's prove this. If you want to prove something like this equality, you have to prove both containments. So for the first containment, we take a word, something in here. We know what it looks like. So let's, and I'm not going to write this out. Let me just say it. I'll let you write it out as a exercise if you want. Let's take an element in here. And since every generator in here is contained in every single H alpha, this word is contained in every single H alpha by closure. Therefore, this word is contained in the intersection of all such H alphas. So let me just say, take S1, E1 up to SK, EK in subgroup in the left-hand side. Then this is in H alpha, by definition of a subgroup. And so it's in the intersection of that, of each H alphas, also by definition. So that's how it goes. So what about the other direction? What does an element in here look like? How would you take one of these things? That's what's hard. I have no idea. If you're intersecting infinitely many subgroups that contain a set, how would you possibly construct an element, define an element of that? But fortunately, you don't need to. And here's why. So I'm going to draw this Venn diagram like this. And the first thing to notice is that this is a pretty trivial observation. If you don't see it, think about it and it'll click. The intersection of all of these subgroups is contained in every single individual H alpha. So note that the intersection of all these subgroups is contained in H1 and H2 and every single one of them. Okay? Well, the left-hand side is a subgroup that contains S. By definition, I mean, so one of these subgroups, one of these H alphas is the subgroup generated by S, or this is a subgroup containing S. So of course, since it's one of these individual subgroups, it contains the intersection of all such subgroups. And that's exactly what we're trying to show. Is that the intersection of all these subgroups, the intersection of any Venn diagram like this, is of course contained in any individual one of them. Isn't that neat? So one of those things that in my experience, students don't see it. It doesn't click. And then if I say it again, I don't get it. I say it again, I don't get it. There's nothing more I can say, but I say it again a little bit slower, and then it clicks, and they get this aha moment. This happens in a lot of areas of mathematics, but a lot of problems, but especially with this proof. There seems to be this kind of binary, I don't get it, and then light bulb goes off, and I get it. Okay, so in summary, the subgroup generated by S is, by definition, by construction, the smallest subgroup that contains S. And we can think of it two ways: as being built from the bottom up, that's what the left-hand side is, this element definition, or as being built from the top down, that's what this intersection definition is as well. Throughout this video, I've used the term subgroup lattice a number of times, but I haven't actually told you what a lattice is. So a lattice is a partially ordered set, such that every pair of elements x and y has a unique supremum, or least upper bound, and a unique infimum, or greatest lower bound. We often write that as with these or and symbols. Now, if you don't know what partially ordered set is, rather than define it, let me just give you some examples, and I think you'll probably recognize it. Examples that we are familiar with, and I'm assuming you've probably seen at least one of these, are subset lattices and divisor lattices. So with subset lattices, we take a set, here's one of size 3, and we take all possible subsets. We put them in a graph like this, and there's an edge between two subsets if one of them is contained in the other, and there's nothing properly between them. So here, 1 is contained in 1 and 3, but it's not contained, so it's not comparable to 2 and 3. We can think of going up as being larger. So this is larger than all of the subsets, and this is larger than these 3, but it's smaller than this, but it's incomparable to these things. That's what the partial order is. So a total order is like the integers. Given any two of them, you can always say one of them is bigger or smaller than the other if they're equal. But here we can have pairs that are incomparable. The supremum of two elements, in this case, is just the union, the x union y. So given any two of these subsets, we can say what is the smallest thing that's above it, and that's the union. And what's the largest thing that's below it? That's going to be the intersection. And that's what motivates these symbols for least upper bound and greatest lower bound. For the divisor lattice, again, I think you've probably seen this in grade school at some point. With an example, here's 24. We take all the divisors of 24 and list them below. And now we have a line between two numbers, A and B, if A divides B, and there's nothing properly between them. So 6 is less than, well, I don't want to say less. So 6 is comparable to 12 because 6 divides into 12, but 6 is not comparable to 8 because 6 does not divide into 8. So 6 is less than 8 in the natural number sense, but in the order inherent in this lattice is, we say that A is less than or equal to B in this if A divides B. And so, by the way, if you're curious, a partial order is is a binary relation like this that is, let me start with reflexive, which means that A is everything is less than or equal to itself. Symmetric, now anti-symmetric, sorry. Anti-symmetric means if A is less than or equal to B and B is less than or equal to A, then A and B have to be the same. And then transitive. I think you know what that is. Every sports fan knows transitivity when they try to compare which team is better than which other team. So that's what transitive is. And you can also define this with the strict binary operation. So reflexive is A is not strictly less than A, and antisymmetric has an analog as well. If A is, I won't go into it. I'll let you look it up if you want. Going back to groups now, the subgroup lattice will be reminiscent of the subset lattice. So we have a group G, but we don't include all subsets of G in here. We just include the subsets that are actually subgroups. So the intersection of two subgroups, notice, is by definition, the largest subgroup contained in both of them. Their union, H union K, is not a subgroup. Well, unless one of them contains the other. But it generates a subgroup. So we can say that the subgroup generated by the elements in H and the elements in K, using the notation from the previous slide, is the smallest subgroup containing both of them. So if we have H and K in the subgroup lattice, just by inspection, we say, what is the smallest thing contained in both? And what's the largest thing that contains both? And the property of this thing being a lattice means that these are unique. And we should hope so. We should never have a subgroup over here that also contains both of them. Well, we could have something like that. But if we did, this would not be the intersection. The intersection, this thing would be something else like N2, and then the intersection would be below these things. And similarly, for any two subgroups, there should be a unique smallest subgroup that contains both of them. Let's prove a short proposition. Every subgroup of a cyclic group is cyclic. And I'm not going to assume that the group is finite. So it's either isomorphic to Zn or the integers z. To prove this, let's let H be a subgroup of G, which is cyclic. And let's assume that H has order bigger than 1. Otherwise, the result is trivial. The trivial group is cyclic. It's generated by the identity. So note that since G is cyclic, every element can be written as a power of X. Every element in H can as well. So H is some subset of powers of X. So let's write that. Powers could be positive or could be negative. Now, of course, if this is a finite group, we can assume that the powers are all positive. But this could be the infinite cyclic group. So let's let x to the k be the smallest positive power of x in H. And there will be a positive power, because if this is non-trivial, if there's a negative power, x to the negative something, then its inverse is x to the positive something. So what are we going to do? What's the plan? We'll show that all elements of H are some power of this. So what does that mean? That means have the form x to the k to the m, which is just x km, for some natural number m. So we're taking the smallest positive power of x, and we're And when I say we'll show that all elements have the form, that really just means that H is generated by x to the k. And m could be positive or negative. So how are we going to do this? Well, let's take some other element of H, anyone at all. So let's call it x to the L in H. And let's just assume that L is positive. Because again, if L is negative, if x to the L is in there, x to the negative L is in there. So we're just going to consider positive L. We can use the division algorithm to write L equals QK plus R. So we can divide K into L. It's got a quotient and a remainder. I'm sure this comes up in like an intro to proofs class. I never remember which one. So and the property with this, for some R, where R is strictly less than K, but at least 0. So here's what we have. And let's do some scratch work up here. X to the L equals x to the QK plus R. And so what are we trying to do? Well, we're trying to show that this is just equal to x times something to the k. So x q to the k. So if we can show that, that's just x to the k times q, and that q is that m right there. So we want to show that this arbitrary element we took is some power of x to the k. Okay, so what's next? Well, let's write that down, even though so x to the L equals x to the q k plus r, and we can write this as x to the, or we can solve for x to the r and write that as x to the L minus qk. This is just laws of exponents. You can see it up. Let me just, if you don't see it now, this is equal to x q to the k, sorry, q times k times x to the r. And if that's equal to x to the L, then we can just, move this over to the right-hand side like you would in algebra. Okay, so now what? This is x to the L times x to the minus qk. This is x to the L times x, and we're just playing around with algebra now, x to the minus k minus q. Okay, so what have we just done? We know this thing is in H. By definition, that's how we picked it. We know this thing is in H because we took something in there. So this product is in H by closure. And what is that product? That product is x to the r. But we picked k to be minimal, and r is less than k. Or k was the smallest positive power, and r is smaller than k, so it can't be positive, it's got to be 0. So by minimality, r equals 0, and that's exactly what we wanted to show. So when r is 0, that means that x to the L is x to the kq, which is x to the k q. So in other words, the arbitrary element in H that we picked is some power of x to the k, which means that H is cyclic. So thus, H is cyclic. And that's the proof. Here's an important corollary. And by the way, this is the typed version of what I just wrote. If we take the group of integers and take the subgroup generated by k integers, so I mean like literally the subgroup generated by a1 up to ak, we know that that is cyclic. We just proved that. So it's generated by some d. And what is that d? Well, it has to be a divisor of all of these things. But it also has to be the greatest common divisor as well. And here's that statement written as a corollary. It's really a corollary to what we proved in the last slide. Let's just do an example. Here's Z24. This is generated by 1, and by anything else relatively prime to 24 in the set. The subgroup generated by 2 is the set of all multiples of 2. So this is, think of this as 0, 2, 4, 6, all the way up to 22. The multiples of 4, 0, 4, 8, 12, all the way up to 20. And the multiples of 8, this is 0, 8, 16. And then the multiples of 3, 0, 3, 6, 9, 12. Yeah, I'll write these all out. Why not? 15, 18, 21, etc. So how many multiples of 2 are there in this set? Well, there's 12 of them. That's 24 divided by 2 is 12. How many multiples of 3 are there in this set? Well, there's 8 of them. That's 24 divided by 3, and so forth. So how many multiples of 12 are there? So it's just 0 and 12. That's 2. That's 24 divided by 2. So think on the bottom, you can put 24 there if you want to make the pattern a little nicer, but 24 is equal to 0 in Z24. So the subgroup lattice of a cyclic group, a finite cyclic group, is isomorphic to the divisor lattice over here. And we can read the order of each subgroup off of the divisor lattice. Let's finish with a useful shortcut that we'll use throughout this course. Often, we'll need to verify that some subset of a group is actually a subgroup. As we know so far, this requires checking 3 properties: that it contains the identity. For any element in H, its inverse is in H. And then for any 2 elements in H, their product is in H. We don't need to check associativity because that is inherited from the group. However, there is a shorter way to do this. And this is called the one-step subgroup test in comparison to the 3-step subgroup test. It says a subset H of G is a subgroup if and only if the following single condition holds. For any 2 elements, x and y in H, x, y inverse is in H. Let's prove this. So the forward direction. So if and only if. So we're going to first prove this direction. So let's say that H is a subgroup. Let's say that H is a subgroup of G. And then pick x and y in H. Then, well, because H is a subgroup, y inverse is in H. And so by closure, x, y inverse is in H as well. And that's, so if H is a subgroup, of course, these 2 elements are in there, so this is in there. The converse is really the non-trivial part, is that this condition is sufficient for showing that H is a subgroup. So let's suppose, let's call this condition star. Star holds. And take any element H in big H. We have to show, right now, we have to show these 3 conditions. So why does H contain the identity? And remember, we can use this condition. So let's take X and Y to be both equal to H. So then by that condition above, we know that X, Y inverse, which is E times E inverse, which is E, is in H. So, okay, H contains the identity. What about inverses? So again, we want to use this condition to show that H inverse is in H. So let's take X to be equal to E and Y to be equal to H. Yeah, Y to be equal to H. By star, we can say that X, Y inverse is an H, but what is X, Y inverse? That's E times Y inverse, which is Y inverse, which is an H. And that's that. And finally, closure. We need to show that if we have two elements in H, so let's take H1 and H2 in H, and we need to show that their product is in H. And the condition that we can use is we know this. We know that H1, H2 inverse. Well, for any two elements, we can apply this condition. So let's let X be equal to H1 and Y be equal to H2. So then by the star condition, X, Y inverse we know is an H, but what is X, Y inverse? Oh, sorry, let's let Y be H2 inverse. So X, Y inverse is H1, H2 inverse, inverse. We know that is an H, but what is that? That's H1, H2 is an H. And there's the last condition. And that proves the one-step subgroup test. Now, sometimes this really is a shortcut. Proving this is no harder than proving closure, and you don't have to show these two things. Whereas other times, you actually, to prove this, you actually have to first prove inverses. And it's not much of a shortcut anyway. So in other words, once you do this, you actually have to prove the identity in inverses to get there. So sometimes it's a shortcut, not always, but it's good to know because when it is, it can save you a little bit of time. It's usually not too hard to show that something is a subgroup. So this is more convenience than anything. Okay, so that's the end of the lecture. We saw a couple of subgroup lattices, those of both groups of order 4 and of order 6. And the next lecture, I'm going to show you a whole bunch of subgroup lattices. I'll show you all of the lattices of groups of order 8, of order 12, there's 5 each, and then at least a dozen more. And so I think you're really going to like it. There's a lot of fun pictures and not nearly as many proofs. I think there might not even be any proofs in the next lecture. So it's a little bit of a contrast to this one. Hope to see you there.